A few things about unsupervised learning with neural networks, insisting on theoretical aspect and also practical application to biological systems of data. So I'm very unsure about, what you could be expecting from me or what I should do, or so whether actually what I'm going to tell you is maybe too easy, too simple. But anyway, one thing I would like to say is that it's certainly biased. Okay, so what I'm going to tell you is to pick up some papers or some works, some ideas or results which I find interesting in the field, starting from the 80s to much more recent works. And of course, this is not a general review of the field, but some things which I think had some impact. So, so what I'm going to tell you about is, let's say, at the crossroad between different fields. One field is statistical inference in a very broad meaning, including machine learning. Another one is statistical physics, obviously. And the third one is about computational biology. So it's written here, systems biology, but what I mean is computational biology of systems, in the sense that we want to study, behavior of biological systems from data and infer some properties of these systems by analyzing the data. Okay, so what do I mean first by unsupervised learning? So you had a lecture by Pier Francesco some months ago. So I don't know if all of you assisted to the lecture or not. So I'm assuming that there is some kind of orthogonality here, but maybe I'm wrong. So what I'm going to talk here about is not supervised learning, which is more related to the perceptron kind of things that Pier Francesco told you about in a different framework for glass transition and so on. But it's more about unsupervised learning. So first of all, what is the difference? So when you have a problem where you want to learn from data, there are different ways of conceiving what the learning should achieve. So here's an example. So for instance, you may be given some images, some pictures of different objects. Let's say, for instance, you have two classes of objects, chairs and sofas. And what you would like to do, for instance, is to train a machine which as an input is given one of these pictures and will produce an output, and the output will be the classification, whether it's a chair or sofa. Okay? So the machine will have some parameters. The parameters will have to be learned from a list of examples. So a list of examples will be a list of input outputs. So each input will be annotated by the correct output. And then the question is whether after the learning phase, whether if you present a new input, whether the machine will be able to associate the correct output. So this is the problem which is called supervised learning. It's supervised because you know what the machine should output. Okay? And the question is how many examples, or what are the good learning algorithms you should use, what are the good machine architectures which are adequate to perform this task. So supervised learning, in a way, is just a fit of input-output relations from examples. And what makes this problem very interesting is that the fit is done in very high dimension. But it's basically a fitting problem, as we do when we do fit a function depending on one parameter, except that here you may have millions of parameters, which makes the problem very hard. So there are a lot of very interesting questions about this supervised learning and a lot of recent works, breakthrough and so on, but this is not what I'm going to tell you about. I will be interested in another problem, which is called unsupervised learning, where actually you are given some inputs, but you are not given the outputs. So you don't know what the outputs are. So I give you some pictures, and the machine will learn these pictures, or let's say we learn some kind of distribution over the pictures, and will produce some kind of representation. And actually, what you are interested in is to produce nice representation, which can be useful for many different tasks. So let me be a bit more precise about that. So one example of representation is, for instance, clustering or dimensional reduction. So suppose you are given your inputs, and these inputs, for instance, if there are images, they could be turned into very high dimensional vectors of pixels, so with colors, for instance, a very high dimension. So you are given some vectors, and you don't know that the vectors have different colors, in the sense that they may have different meanings. So maybe you have a set of points here which represent chairs. Here they represent sofas, or here they could represent another piece of furniture, whatever. So you are given these points, and the question is whether you can actually let's say, unveil some underlying structure in the points. So for instance, here in this example, so these points are in a very high dimensional space in principle. 3 dimensions are represented here. You could imagine that if you choose in an adequate way the axis of representation, then you get a nice way of representing the data where these clusters may emerge. Okay? So basically the task here to be done is to find a low-dimensional representation of the data where the structure can be seen easily. So this is actually what I'm going to tell you about today, especially dimensional reduction. So this is a very important task in unsupervised machine learning. Okay, so you are given points, but you are not given outputs about what these points mean, actually. So what the goal is to find the underlying structure. But there are many other interesting tasks and very fundamental problems in unsupervised learning, which I will talk about in the future lectures. Find adequate representation. If you are given this data, there might be ways of representing the data which are very useful to understand what the data mean and also to process the data. So for instance, you may represent numbers in Roman numerals, but this is not very adequate as a representation. It's a fine representation, I mean the meaning is there, but if you want to process, that means do operation, multiplication and so on, the Arabic system, Arabic numerals are much easier to deal with, right? So representing a nice representation can be very useful in order to do something with the data. So machine learning, unsupervised machine learning can be useful to do that. And another task which is very interesting and very important also in application is actually the generating aspect of the models. If you are able to represent the data and actually disentangle the different components of the data, their distribution, maybe you can actually use this knowledge, which is inferred from the data, to generate new data. So there are different aspects here. You can, for instance, be given a time series of data and you would like to be able to predict future, so generate new data. Or, for instance, you are given all these chairs and you would like a machine which is able actually to produce new, nice-looking chairs, but these chairs were not in the database, right? There are different ones. But if you understand what a chair is, that is, you need you know, some kind of horizontal plane here, you need 4 legs, and you need you know, all these kind of components of a chair, and then you can actually play with that and generate new chairs. So this is where the idea of having nice representation is very important. Okay, so today I'll talk about only one aspect, dimensional reduction, which is important actually and which is useful. And I will go back to very old papers from the 80s and 90s to show you what has been done in the framework of statistical mechanics and also machine learning. So basically, the problem I'd like to talk about today is actually a very simple problem in practice. I mean, in terms of definition. You have a set of very high-dimensional data, and there are some directions in this very high-dimensional space which matter. They are more interesting than other ones, and we like to infer these directions. So what do I mean by that? So this is actually the goal of principal component analysis. So I will briefly, I don't know if everybody is familiar with principal component analysis here. It's a very basic tool in statistical analysis, but I will just briefly recall you what PCA is. And then the kind of phase transition which are present in principal component analysis. And then I talk about a specific neural implementation dating back from the 80s, which actually achieve principal component analysis. And we'll understand more, I mean, some generalization of principal component analysis to more interesting cases using statistical mechanics of these other systems. And these are works which we have done in the 90s. And we'll talk about how we can beat the phase transition threshold here by using prior information about the direction we want to find from the data. And then if I have enough time, I'll talk about a nice application, which is the study of memory consolidations in rats. Okay, so let me start with the framework. So usually when people apply principal component analysis, they don't care so much about having a nice probabilistic framework where everything is justified, but I think this is useful here. So I will assume I have some data which are generated from some multivariate Gaussian distribution. And I am assuming that all the means of the variables are equal to 0. So they are centered variables. So psi will be one of these data points, which is an n-dimensional vector. And this is the multivariate Gaussian distribution. So tau, the inverse of the covariance matrix, is called the precision matrix in statistics. And this is essentially minus the interaction matrix in statistical physics. Let me use the pointer here. Yes. So this is the n by n matrix. And of course, you have one very simple case, which is the null case, where, say, tau, this inverse covariance matrix, is just the identity matrix. In that case, that means that all the variables are just independent from each other. So this is a nice, interesting null case that we will study. But in general, tau can be any kind of positive matrix. And what we do, I will assume I draw randomly and independently from each other p samples from this distribution. So what we have is a set of p n-dimensional vectors. And we would like to understand something about the structural data, that is something about this tau matrix from this set of configurations. Okay? So, so in the null case, where tau is just the identity matrix, the covariance matrix is also the identity matrix. It's just the inverse of the precision matrix. So sorry, it's not p by p, it's n by n. It's a mistake here. And if I represent some data here, so in the, let's say for instance, here it's just a 3-dimensional representation, but you could imagine it's an n-dimensional representation. You have the axis here. Then the cloud of points, of data points, will generate typically a sphere of width 1. That means that the standard deviation of this data is 1 along all directions. So we get some kind of spherical shape here. So now, if we have a more interesting precision matrix, where, for instance, one direction is different from the other one, and this can be achieved, for instance, if the eigenvalues of the precision matrix are not all equal to 1, but one of them, for instance, is smaller than 1. And I will use this formula that tau is the identity minus s over 1 plus s times the projector over E. And this is a projector over some direction. So E is a normalized vector in the n-dimensional space, where s is a positive number. Then the inverse of this precision matrix is the covariance matrix. And this is the identity plus s times the projector along E. Okay, so s is here a positive number, but actually most of what I'm going to tell you is also valid for negative s. So what happens if we generate data from a multivariate Gaussian distribution with this tau precision matrix? Well, what we'll have now is that the cloud of points will have a lot will have different extensions depending on the direction. So along E, the typical extension, the standard deviation, will be given by the square root of the eigenvalue of C corresponding to this particular eigenmode. So E is an eigenmode. And this is square root of 1 plus s. So if s is positive, this is larger than 1. While along all the other transverse direction, all the eigenvalues of C are equal to 1. So we get the same extension. So we have more extension along this direction. And this is the idea of principal component analysis. If in a very high dimensional space you have some directions where the points are more scattered than along the other directions, then these are the direction you should retain. Because there are more ways to distinguish the different data along this direction, right? While if you have, for instance, a very narrow direction here, then all the data give you essentially the same value d. Let's say projected d will be essentially 0, so you don't learn anything from data from this projection, right? So the idea of PCA is actually to find the direction where this cloud of points is very extended. Okay, so how do we infer E from the data? So let's go again to the probabilistic framework. So we have the data points, which are drawn randomly from this distribution. So what I would like to do now is to use Bayes formalism. So are you all familiar with the Bayes formula? Yes? Right? So essentially, I'm generating the data with this thing here. So this is the likelihood of a precision matrix given the data. This is the probability of the data given, or density probability of the data given tau. Okay? And so what is going to be the posterior probability for my precision matrix tau? It's going to be the probability of all the data, that is the product of a mu of all these densities, because I'm assuming the data are drawn independently from each other, times maybe some prior over tau, prior probability. And I will consider this prior probability later on, but now I can assume it's uniform. I don't know anything about tau. And this defines, once properly normalized, the posterior distribution for tau. Right? So the posterior distribution for tau is proportional to the product of a mu of rho of psi mu given tau. And when you basically do the product of a mu here, it's a sum of a mu here. And using again this expression for tau, what you find is that the E dependent part of the posterior distribution is this one. That's the only place where E is present. And we see if we want to maximize the posterior probability of the vector E, what we have to do is to maximize this term over E, where E is a normalized vector. And it's obvious that what we have to do, it's the sum over mu here, sorry. What we have to do here is to find the largest, or let's say the top component of this matrix here, which is the n by n correlation matrix, computed from the data. So it's the empirical correlation matrix computed from the data configuration. Is it clear? So what I'm saying is that it's very simple. You have all your correlations, all your configurations, sorry. Psi mu. So I is the dimension of the space, so that's it goes from 1 to n. Mu is the index of the data, 1 from P. And I'm computing the correlation matrix, the C hat ij, which is 1 over P, sum over mu, psi mu, psi j mu. And what I would like to do now is to find E, is to find the top eigenvector. Of E, of C hat. And this will produce some vector E hat. And I'm assuming, I'm hoping that this is actually the nice direction where something is interesting is going on in that very high dimensional space. Okay? This is what PCA is doing. So it's a very simple thing. It's nice because it can be done, in a time which is polynomial in n. So it's an algorithm which is used by many, many people. And actually, you don't have to restrict yourself to a single component, but you can infer maybe 2, 3 components just by taking the k top components of C hat. So let me show you, for instance, one example of that. So here, for instance, is a famous database in machine learning that's called the NLIST database, which is just a data set of handwritten digits from the US postal data. So you have about 60,000 digits, which are represented on 28 by 28 pixel images. And you see 2, 9, and so on, all the digits from 0 to 9. And what we can do is actually use this data, compute the correlation matrix here, and see what are the top components. So of course here I'm losing all my Gaussian framework. This is not justified at all. This is just some kind of recipe. But anyway, we can do that. And if you do that, this is the kind of top component you get. So this is again represented as a 28 by 28 representation, but you should think of that, about this as a vector in the 784 dimensional space. Okay, so let me take, for instance, the top component. So you see, this is the top component. So the blue color corresponds to positive entries and the red one to negative entries. And what I can do is then, along this direction here in the space, I can project all my points. Okay, I have this cloud of points here. I have all my 60,000 digits. I can project along this direction, which is identified by PCA. And this is what I get. Actually, I do that for the first two components here, the first one and the second one. And along the first one, you see some kind of clustering going on. And here we have projected only, actually this was done by Jérôme Toubiana, who is doing his PhD at ENS right now. What you see here is we have looked only at the zeros in the database and the ones in the database, and you see a nice projection here which divides the two clusters, and this is pretty clear from the shape of this vector. You see, a 0 looks like actually the red entries here, so it will have a very strongly negative projection. While a 1 corresponds to the central part, which has positive entries, and that corresponds to the positive things here. I'm sorry about the fact that the colors are exchanged with respect to that. Okay, but anyway, so the red points here correspond to the 1s, and the blue points to the 0. So you see, you have these complicated things, and actually by projecting the images along one direction, that's enough to distinguish the 0s from the 1s. So the data are not so complicated from this point of view. Of course, if you want to distinguish 8s from 3s, this is a more complicated thing you have to do. And you have to go to high dimension to see this clustering going on. But I will show you at the end of the lecture a much more interesting application than this thing, okay? It's just to give you some idea. Okay, so now the question you may ask, actually, from a statistical point of view, is that assuming that there is a nice, interesting direction in the n-dimensional space, and now assuming that we draw randomly p examples from the Gaussian distribution, will the E hat direction here be close to the ground truth direction? Okay? So again, I'm assuming that I'm drawing example from this distribution where there is actually some kind of symmetry breaking. So one direction is actually different from the other ones. Okay? It corresponds to a different eigenvalue of a covariance matrix. I'm taking these P samples, I'm diagonalizing this, and now I'm asking whether the top component of this empirical correlation matrix, is it aligned along E or not? Obviously, if P is extremely large, this is obvious, because this will be actually the population covariance matrix. It will be just the inverse of tau, and we will find E very easily. But if P is not so large, in particular compared to N, this is not an obvious thing. Okay, so this question was asked by many people, and you can get some intuition about what is going on, and then I will go to the exact results. The intuition is the following. So let me consider the case where actually there is no interesting direction. So what I get, what I consider here is the precision matrix tau, which is just the identity matrix. So all the variables psi I are independent from each other. So if I consider the correlation matrix C, which is the inverse of tau, all its eigenvalues are equal to 1, obviously. Now, if I draw randomly P samples from this distribution, and I compute this empirical covariance matrix, then this won't be the identity matrix, just because I have some sampling noise. Okay, so it will be some kind of thing, some matrix which is close, if P is large, but not exactly identical to the identity matrix. So that means that if I compute the eigenvalues of this empirical covariance matrix, I won't find that all the eigenvalues are close to 1, but I will find some extended spectrum around 1. Okay? And the question is what this spectrum looks like. So I won't do the derivation here, because I'm sure, I guess many of you have heard about the Martian-Pastor spectrum of random correlation matrix. So this, it is not very complicated derivation, actually. But I will just give the result because this is not the main topics of my lecture. Okay, so there is a well-known result, which is known as the Martian-Pastor spectrum, which is given by this formula. This is the density of eigenvalues for this empirical covariance matrix when you have no correlation between, I mean, in the sense that the precision matrix is the identity, so all the variables are independent. And this spectrum is actually given by this quantity here. So lambda plus and lambda minus are the edges of the support of the spectrum. And they are given by these formulas, 1 plus or minus square root of r squared, where r is the important ratio. This is n over p. This is the number of variables, so the dimension of a space divided by the number of samples. So very well sampled situation correspond to the case where p is much, much larger than n, so r is going to 0. So in that case, you see that lambda plus and lambda minus coincide with 1, and we find back the Dirac distribution in 1. Otherwise, in situation where p and n are comparable, then r is a finite number, and you get a spectrum with some width. So let me show you some examples. So obviously the spectrum, so I should be a little bit more careful here. This formula is correct for r smaller than 1, so when we have more samples than dimensions. If r is larger than 1, this is a bad situation, which is very much undersampled. Then, of course, since the rank of the matrix is at most p, that is, you have at least n minus p eigenvalues of the matrix equal to 0. So on top of this distribution here, I should add a peak in lambda equal to 0 with a mass equal to 1 minus 1 over r. So let me show you what we get, for instance, when we represent the curve. So this is for r equal to, so this is lambda here, and you get rho of lambda. For very small r, you get a distribution here, which is peaked around lambda equal 1. And in fact, this is essentially a semicircle distribution. For r very, very small, we can forget about the correlations between the different elements of the matrix. They are very weak. And asymptotically, for r going to 0, I get a Wigner distribution with some appropriate width here, which is of the order of square root of r. Otherwise, this shape is not a semicircle shape. It's totally asymmetric with respect to lambda equal 1. And as r gets bigger, you see it gets wider and wider. In particular, the top eigenvalue can be extremely large, very far away from 1. It's 1 plus square root of r squared. Okay? So that creates a problem, because obviously if my top eigenvalue here is large, then that should be compared to the top eigenvalue from the true covariance matrix, the one I would get if I had an infinite sampling, which is 1 plus s, where s is in my parameter. Remember, this was the eigenvalue of this correlation matrix. 1 plus s here. So it's obvious that if the spectrum extends too much, then it can essentially touch this eigenvalue here, and then I may actually be in trouble, because if I infer, for instance, the top eigenvalue here, suppose, for instance, this thing extends over 1 plus s, then the top eigenvector I will infer here is just coming from a noise, okay? It has nothing to do with the signal eigenvector with E, what the direction I would like to infer. So this thing can be made more precise, and essentially there is a phase transition which separates two regimes. And here I'm citing the results which were rigorously proven by Baik, Ben-Arous, Péchet in 2005. But then I will give you the derivation which was done 10 years before by people in statistical mechanics, which is actually a more powerful framework which can handle other cases, more cases. I will give you that if I have enough time on the blackboard. This is my goal. So I'm just citing the results, but you will see how they can be found out. So if we are in a regime of weak noise, and weak means here R is smaller than S squared. So again, the size of the matrix N goes to infinity. The number of samples goes to infinity. They both go to infinity, so it's a double limit, infinite limit. At a fixed ratio, R equal to N over P. So if R, which is the amount of sampling noise, is smaller than S squared, so S is the deviation of the eigenvalue with respect to 1, so it's essentially the strength of the signal. So if the sampling noise is smaller than S squared, and that does not depend on the sign of S here, then we are in a good shape. We have enough samples to actually detect the interesting direction. And if we diagonalize this matrix here, then one eigenvalue will be expelled from the bulk here, the noisy Martian copastor bulk. And this corresponding eigenvector is aligned along the true direction. So I will tell you in the next slide what it means aligned. And in the bad situation, when the sampling noise is too large, larger than S squared, then what we get here when we diagonalize is simply the Martian copastor spectrum. And the top eigenvector here is essentially uncorrelated with the interesting direction. This phenomenon that actually you need a minimal amount of samples before you are able to detect anything was called retarded learning in a series of papers by statistical physicists in the 90s. You know, I mean, you could think that as soon as you get a little bit of data, so you want to find this direction, so you start from nothing, and then you get a little bit of data, and then you start aligning along the direction. But that doesn't happen here. You need a minimal amount of data, which is given by this threshold here. Okay, so in this situation, what is the top eigenvector? Actually, the overlap between the top eigenvector and the true one, which is the one in the defining the tau matrix, can be computed, and this is given by this formula. So just to give you just a representation, for s equal to 0.2, for instance, we have a critical ratio n over p, which is 0.2 squared. So if the number of samples p is smaller than these things, so n over 0.04, the overlap is equal to 0. So essentially we have the true direction here, and what we infer by diagonalizing this matrix is orthogonal. And then if we are below this threshold here, so we have more than n over 0.04 examples, then we start aligning. And the more samples we have, the closer will be the two vectors. Is it clear? No? Okay, so I will discuss how this result can be found in a more general setting. But before I do that, I would like to talk about the practical implementation. So of course, you can, in order to find this top eigenvector, it's very easy to write down the matrix and diagonalize it. I said it's fast. Well, it's fast, but I mean, by fast, I mean polynomial in n. Takes the time which is, you know, if you want to get all eigenvectors and cube, if you want to find the top eigenvectors, maybe you can use Langsch's algorithm, which is essentially start from a vector and then iterate c hat times a vector and so on project path and so on. And this gives you a time n squared. Well, so this is fine, but I would like to, since I'm supposed to talk about neural nets, tell you how actually these kind of things can be done with neural networks. And there is a famous paper by Oja from the 80s where this was done for the first time. So this is the paper. And the interesting thing about this paper is that the way the algorithm I'm going to tell you, which is very simple, is actually doing unsupervised learning. It's doing this thing, finding the top component. But it's really based on the idea that the computation one is allowed to do that should actually be plausible from a biological point of view. And I think that was interesting because this is the time where, at the end of the 70s and beginning of the 80s, people really wanted to have biologically plausible algorithms. So there was really people from the two cultures mixing together. So this paper was very influential from this point of view. So I'd like to discuss this thing. So what was the idea of by Oja? So it's a simple idea. So what is that? The neural network, which is going to do the calculation. Actually, it's a single neuron, essentially, very similar to the perceptron architecture Pierre-Francesco told you about some months ago. So here you have a list of input. You have a set of inputs, xi. So I use x and not xi because this is the notation in the paper. So if people are interested in looking at the paper, so they will see the same notations on the slide. So we have n inputs, xi running from 1 to n, which are real numbers. And here we have a single output neuron, which I call y. That's the value of a neuron. And what this neuron is doing is basically computing the weighted sum of the inputs. So it's a linear neuron, the simplest neuron you can think of. I mean, realistic neurons do more than that. They have some non-linearities. Well, not all realistic neurons. Some realistic neurons, some real neurons actually are quite linear in some specific region of the brain. But here, actually, what the neuron is doing is just computing the sum of I, wi, xi, where wi is the weight of a connection between input I and the output. So I will simply denote this by w.x. So Oja's idea is that this neuron will be presented, these examples, one by one. So it's not that, in order to compute this matrix, you are given all examples together. So you have at your disposal all this example, and you compute the matrix. And then you diagonalize it. Here, the idea is different. We do some kind of online learning. The neuron is given the example one by one, but there is no memory effect. So once an example is exploited, it's not seen again. You cannot memorize it somewhere and look at it again. Okay. So when I say no memory effect, I'm cheating a little bit. Actually, all the memory effect is actually in the dynamics of the weights. So the neuron will adapt its weight, so will learn the data by changing its conformation. So how can it learn the weights? And so this is where the biology is coming in. So the idea of the dynamics of the weight is called Hebbian learning. So what is Hebbian learning? It's actually a concept which was invented a long time ago. So especially which was formalized in this very famous book by Donald Hebb in 1949. And here is the citation that you can read from the book. And essentially the idea is this one. It can be summarized here. Cells that fire together wire together. So the idea is that when you have neurons which are active in a simultaneous way, then they will have a tendency to increase the connection linking the two neurons. Of course, if they are not connected by anything, connection will not arise from nothing. But if there is a connection, the connection will grow in terms of strength. While if they are not simultaneously active, then the connection will have a tendency to be depleted. So that means that the weight, the connection, the interaction between the neurons is actually dependent on the activity. So activity at later time will be dependent on the activity at previous time through the change of the connection. So what is the experimental evidence of that? So I just want to mention this because this was postulated in 1949. The paper by Oja is 1982. And actually the first evidences were only, to my knowledge, at the end of the 60s. And they were repeated in the 70s. So I just want to show you two experiments because I think they are interesting. So one experiment was essentially an experiment where people were measuring with electrodes the activity of a cells in one part of the hippocampus. So I talk about, again, about the hippocampus, which is a very specific and interesting region in the brain I think in the last lecture. But here we don't care. I mean, just one particular region of the brain. So the activity on your neuron was measured, while the activity, or let's say the input to this neuron was stimulated here by another electrode. So essentially what you can do here, you measure the result of a stimulation on this neuron here. Okay, so it's important to know what the neuron is doing. So each neuron is basically summing up the different currents, which is collected by the dendrites, which is some kind of tree of connections, receiving all the inputs. And then it will emit some output along the axon, which is this thing here, where this spike or action potential will be emitted and will travel along this wire here, an electrical wire, until a new, it will arrive onto a new dendrite of a postsynaptic neuron and so on. Okay, so the idea is the following. Each time a neuron will receive some inputs from another one, that is done through some kind of complicated things, which is called a synapse. And the synapse strength can be measured by the size or the amplitude of a current which is received by the postsynaptic neuron here. So essentially what essentially that's the thing here. If a neuron actually is not connected to another one, each time the first neuron will emit a spike, the input in terms of increase of potential of a second neuron will be very close to 0. And this is what is going on at the beginning of the experiment. Now, if you stimulate the first neuron a lot, what you will see is that now each time the first neuron here will emit a spike, an action potential, then the increase in the difference of potential between the outer part and the inner part of the membrane of a second neuron, the postsynaptic neuron, will be much larger, about 2 millivolts here. Okay? So that means that there was a modification at the level of the connection, of the synaptic synaptic connection between the two neurons, which is actually lasting for a long time. It can last over weeks. And you see this effect here at very large time, while the stimulation was taking place here only about over a duration of 10 minutes. Okay, so I don't know if I was very clear here, but the idea is that you have a connection between the two neurons. This connection means that each time an action potential coming from the first neuron is traveling here and hitting the synapse, it will create some change in the potential of the second one. Now, if this neuron is summing many changes of potential, it will be enough to get over some threshold and then emit itself another action potential. So you measure the strength of the synaptic coefficient here by the amplitude of this excitatory postsynaptic potential. Okay? So this is 0 before the experiment. When you have a large simulation for minutes here, so this is a very strong modulation in a very high frequency, then you get a strong increase which may last for a very long time. So clearly, the activity has generated a change in the interaction coefficient. And I want to mention more recent experiments, which are much more subtle experiments, where people actually do, so this is the same idea. You can actually pick up with 2 electrodes, 2 different neurons, one presynaptic and one postsynaptic neurons. So the connection is going from the presynaptic to the postsynaptic one. And the protocol of the stimulation is the following. Create a spike of the presynaptic neuron at some time and generate a spike by excitation. I mean, it's a reinforcing of the postsynaptic one after a delay tau. And repeat this process, excitation, okay, many times at a given delay tau. And now stop this protocol and excite the first one and measure the increase in the potential of the second one. And what you see, this is a measure here, in relative measure with respect to what was going on before the stimulation, as a function of a delay tau. So this is t pre minus t post, so negative, okay, so this situation here is actually corresponding to a negative time, because t post is larger than t pre. Okay, so you see that if you stimulate first the presynaptic one and then the second one, there will be a tendency to increase the synaptic coefficient if the delay is, let's say, smaller than 40 milliseconds. If the delay is too large, there will be no effect. If you do the opposite, that is, you are basically violating causality, you are stimulating the postsynaptic one and then the presynaptic one, then what is going to happen is that the synaptic coefficient will decrease. Okay, so there are a lot of measurements now in neurobiology. So I just want to say that this Hebbian learning rule is actually quite subtle, but there are some basis to it. Okay? So now I will go back to Oja's rule. But I just wanted to mention this result. Okay, so what is the idea about Hebbian learning? So this is exactly that. I'm assuming there is some kind of discrete time dynamics. So the weight vector will depend on time t. And it will be updated according to this scheme. The weight vector at time t plus 1 is the weight vector at time t plus some modification. The strength of the modification is controlled by some parameter, eta, which is called the learning rate. So it's a small number. And here we have two terms. One is the Hebbian term. So the Hebbian term is the product between the output and the input. So if both are positive, so this has to be seen component by component, then that will strengthen the connection. If one is positive, the other negative, will deplete the connection. Okay, this is the idea. And there is another term, which is not a Hebbian term, which is called a leak term, which is depleting the weight vector here with some strength here, which depends on the output magnitude. So it's the output squared. So we'll see what they mean. Okay? Is it clear? So this is the dynamics. Now I want to show that this dynamics is actually extracting the top component of this matrix. But again, we are presenting at time t here, this is the mu pattern. So this time t is essentially the index mu here. So I'm inserting data on the input layer. The weight vector will adapt according to this equation, and then I'm inserting new and new data. But I cannot go back to the old data, okay? It's gone forever. So I will have to show you on the blackboard how we can analyze this dynamics, which is not so complicated, but actually it turns out the rigorous proof of what this dynamics is doing was published last year in 2017. So although this looks very simple and people had known for about 30 years what is going on, this was not proven. So I won't give you the proof, I will just give you the ingredients, what is going on. Okay, so let me copy the equation, or maybe you have the equation on the slide, so I don't need to copy it. Okay, so just as a starting point, we can make a remark and compute the norm of the vector and see how that it is updated over time. So if I compute the norm squared, so wt plus 1 squared, this is the norm of the first one, of the at time t, sorry, plus some linear term in eta, which is going to be 2 eta, and then I have y of t, wt xt, minus yt squared times wt squared. But of course, wt dot x is exactly yt, right? And then there are terms of the order eta squared. And I will assume that these terms are not very important. In fact, I will be interested in the limit where eta goes to 0. And the time t, that is the number of examples which are presented, goes to infinity. But the product should be of the order 1. I'll go back to that later. Okay, so this is simply 2 eta yt squared, 1 minus wt squared. So you see what is going on. If I start from w's which are, let's say, very close to 0 weight and so on, or let's say very small, then wt will increase until it reaches essentially a norm equal to 1, and then it will saturate. Okay? In fact, this rule here by Oja is, let's say, one approximation of, let's say, hard rule which imposes in a hard way the constraints of normalization of the weights. And this hard rule is simply that you could have as an alternative, and sometimes you may find it in literature, that, for instance, you start from W0, which is normalized to 1, and then you apply an updating rule, which is simply Wt plus 1 should be equal to Wt plus eta yt xt over the norm of this thing here. So we see that the Hebbian term is actually the fundamental term. Wt should be turned around this direction, okay? And then you normalize it. Now, if you do that and you expand to first order in eta, you will find exactly Oja's rule, which is over there. So you see that the leak term is a term which is basically enforcing in a soft way the normalization of the weights. Okay? That's the idea. But the fundamental term is this one, the Hebbian term. Okay. So let's see what this dynamics is doing. Okay, so I had data which are extracted from this distribution, which are For instance, the Gaussian distribution I was talking about before. So we have a covariance matrix, which is actually the one of the population. So this is tau minus 1, if you prefer. So this is the average of xi, xj over x. And this covariance matrix is obviously a positive matrix, so I can diagonalize it with an orthogonal matrix. So I can write it as this thing here. Where this matrix here is a diagonal one. So this is diagonal of lambda 1, lambda 2, lambda n. And I will assume that here I have ranked the eigenvalues from the top one to the smallest one. And they are all positive, obviously. But let's say lambda 1 is larger than lambda 2, which is larger than the other one. Okay? Then I'll talk briefly about the case where you have degeneracies, but it's not very interesting. So O here is the orthogonal matrix. So if I change basis, so I go from the canonical basis at the origin to this rotated basis, where I apply O. So that means that I will apply OT to W. I will do the same thing on the inputs. You see that if I do that, the output is actually unchanged because it's just a dot product. Okay. Then the Oja's rule, it's obvious, everything is linear here. Oja's rule means simply in the new basis. So I will keep the same notation, but this is in the new basis now. We have well, we have this thing here. We have WT plus 1. Or maybe I should write it. Well, okay. Yeah. Obviously, in this, okay, maybe I should keep the notation because otherwise it will be complicated. So obviously, in this notation, in the new basis, we'll have simply this thing here. Okay, so I can work in this basis here, and the YT is simply WT prime dot x prime, which is the same thing as WT xt. So I will drop the subscript in the following, but I just wanted to say that I will make this change of variable. Okay, so now I'm assuming that the x1 and x2 are drawn randomly from this distribution. So this distribution now is has a diagonal covariance matrix. So the distribution of the x prime is a bit simpler than the original one. So we have x prime I, x prime j equal to lambda I delta ij. Okay. And I'm asking what is going on now for the weight. Okay, so what we will do is we will first compute the average change in the weight vector once a new example is given to the network. And then we'll bound the variance of a change. So let me compute the average change. So what is the average change here between the weight vector at time t and at time t plus 1? Condition, for instance, that Wt was equal to some W at time t. So that's the expected value of W of a change in delta W. Well, okay, so so the change is given by this thing here, that's this term here, and now I am averaging over the vectors x. So this is the average value of Wx times x minus Wx squared W. And I'm averaging over x. So I have dropped the prime index, but this is I am in this basis now, okay? So this is a bit simpler, everything is diagonal. Okay, so I can very simply compute the averages here because everything is quadratic and I know the covariance matrix. And when I do that, I see that the ith component of this delta here, so let me write it. If I look at the component I, this is simply given by eta times lambda I wi minus sum of the k, lambda k, wk squared, wi. Okay? So just, well, I mean, it's obvious. So this is the average. Now we can go to the square deviation. So this is the same thing. I'd like to, let's say, bound, let's say, the change in norm. So it's easy to realize. I don't know if I have to do that in detail, but you can realize that the change in norm, so for the change in norm, or let's say the norm squared, square norm here, we can see that actually the change in norm squared, wt plus 1 minus wt squared, this is bounded from above by some term which is order eta squared times the norm of x squared. Well, something like that. So actually, the norm of x squared is not bounded from above by anything. Since I have a Gaussian distribution, I can modify a little bit my distribution of data, where I still keep the covariance here, but I can have some bounds, for instance. And this is going to be good. Since I don't have much time before break, maybe I can leave some notes, handwritten notes, where this is a detail where all these small calculations, which are not very interesting. Essentially, the important point is this is bounded from above by eta squared times something of which is bounded. Okay, so now I will assume that eta is set to 0, so I have a very small learning rate. But then I will present many examples. So it's a very slow evolution of the weights, provided by many, which is fed by many data. So we will send eta to 0 and t to infinity with a fixed product. Tau t eta is order 1. Okay, so now let me look at the evolution of the system. System, I mean the weight vector. Over time interval. Tau plus epsilon. Well, this is small, but again, this is small, but order 1, while eta is going to 0. Okay? So that means this is equivalent to over t equal to tau over eta to t prime equal to tau plus epsilon over eta. So there will be a lot of time steps in between. Epsilon over eta time steps, which diverges as eta goes to 0. So if I look at the difference between the weight vectors, I can write this. So this is a sum over t0, running from t to t prime minus 1, of wt0 plus 1 minus wt0. Okay. And this I can separate into the average value of that plus some fluctuations, with means equal to 0. So this is equal to the average value. So I'm not writing this because this is, condition to wt0. This is the quantity which is here, which I have computed, plus some fluctuations, which I call z of t0. Okay, so what is this term here? This is what was on the blackboard, which I can show here. So this is the term I have computed, which is proportional to eta. So it's a eta times, if I do, so this is order eta. I can put all the components if I want. You have the precise expression here. But this is order eta. And how many terms do I have here? I have epsilon over eta terms. Okay? So these terms are not all equal, obviously, because w will change that. But actually, if I look at this product here, I see I'm expecting the whole thing to be order epsilon. That is, actually, the change in w will be very small if epsilon is small. So if I keep epsilon small and eta goes to 0 much faster than epsilon, I will see that the whole thing here can be actually approximated up to order epsilon squared by exactly epsilon over eta times exactly the same terms taken for t equal to t0. And I will make mistakes of the order, errors of the order of epsilon squared. Is it clear? So I can give you the, so there is a rigorous paper where this argument is done in a clear way by Li, Wang, and Zhang in the proceedings of a NIPS conference in 2017. So I don't want to go into all the details, but this is the idea. Now, of course, if I do that, I'm neglecting these terms here. So am I allowed to do that? So the average value of z is equal to 0. So if I compute the variance of these terms here, if they were all independent, that would be the sum of the variance, epsilon over, so this is the variance, epsilon over eta times eta squared, due to this inequality here, times some constant, so C O eta squared. And that goes to 0 when eta goes to 0. So even if we have many terms like that, they will actually not contribute. So actually we can neglect these terms. So there are some weak correlations, but that they don't change this result here. So I'm just giving you the main ideas. Is it okay? So essentially what we have is that within this limit where eta goes to 0 and t goes to infinity, instead of having some kind of stochastic dynamics, we get some deterministic dynamics for the weight vector. Okay? It's just changing very slowly in a deterministic way. And if I divide by epsilon on both sides here, so I will say that this thing is actually some function w of tau plus epsilon, and this is w of tau. Then by dividing by epsilon, I get an equation for the, I get a first order differential equation for w of tau. And this equation is simply dwi over d tau equal to the term I had computed here, which was, I'm just recalling you, lambda I wi minus sum over k, lambda k wk squared wi. Okay? So this is the equation we get. So I can just give you a solution, and then we make the break. So one thing you can check very easily, if you start at time t equals to 0 with a normalized vector, then this is true for all time. It remains normalized at all times. It's very easy to check from this thing here. Okay? Okay, and then the equation can be solved very easily, and the solution is given by that. Wi of tau is equal to Wi of 0 times exponential lambda I tau over some normalization, which is the sum of the k of wk0 squared exponential 2 lambda k tau. And the whole thing is to the power 1/2. Okay, so now if I increase tau, so as the time goes up, you see what is going on. If lambda 1 is larger than all the other eigenvalues, the whole thing will converge at large tau to delta I1. So that means that this algorithm is just extracting the top component. We are in the diagonal basis here. Okay. So just a few comments. Well, I have some remarks about that. Yeah, maybe I will do the remarks and then we make the break. It's okay. So what the algorithm is doing is essentially it's starting from some. So we have the direction. Now let me go back to the original basis, and this is the direction we would like to find E1, which is the eigenvector associated to lambda 1. When we start from a random value of the weights, with high probability they will be essentially orthogonal to that. I think the dot product will be order 1 over square root of n. So we start in the very close to the horizontal, I mean orthogonal plane here. So maybe W at time 0 will be somewhere here. And the dot product here will be very close to 1 over square root of n. It can be positive or negative, it doesn't matter, okay? Now, since we have some kind of exponential growth here, it will eventually converge to E1. So the whole thing will rotate and will go to E1. And what I have computed is just the dot product at some time tau here. But you see, when n is very large, it will take a lot of time to avoid, I mean, to escape from this orthogonal plane. So everything I've done here is for finite n on tau going to infinity. So it's a kind of normal standard analysis in statistics. You have a finite problem and you have a lot of data. So it's a very nice, simple setting. But you could wonder what will happen if n is actually, if t, the total number of samples, is not allowed to be much larger than n, for instance. This is not actually studied so far, to my knowledge, in this dynamical setting. So we are in the asymptotic setting when we have a lot of data. So indeed, if we are in this situation, you see that the time it will take to go from 1 over square root of n to, let's say, delta, where delta is positive, or the 1 but small, this time will grow, the time will, t, will go like the log of delta square root of n over lambda 2 minus, over lambda 1 minus lambda 2 with an eta here. So it will be large due to the n factor here, but it can be very large because actually the gap between lambda 1 and lambda 2 can close when n is large. So it depends on the nature of the data. So it may take a lot of time to escape this. Then we have this phi dynamics, and then we get again to something here. But here, once we are in this situation here, what is going to happen is that in practice we don't have eta going to infinity and t, eta going to 0 and t going to infinity. In practice, when people run the simulation, they have finite eta, and then they run it for large t's. So since the learning rate is never equal to 0, what is going to happen is that we will have no convergence here. We'll have some fluctuations around E1, and eta will set basically the value of the effective temperature around E1. So in order to avoid this fluctuation, what you can do is to decrease eta with time. And in fact, if we want to decrease eta with time, what we can do is to have eta decreasing as 1 over t, for instance. And that will ensure you that you will converge smoothly to E1. This is what people do in practice. So I have other remarks about that. And I will be brief. And this is, okay, this is going to be my last remark, and we'll make a break. Everything I have said here can be generalized to more than one component. And this was done by Sanger in 1989, so a few years after Oja. And then we get a neural network which is a bit more complicated in terms of structure. So I won't analyze it, but this is exactly the same thing as this one. So the idea is the following. You have an architecture where now you have k different outputs, and you always have n different inputs. So the connection between xi and yl is some weight, wli. And Oja's rule can be generalized to that, to things. So the dynamics now is wli at time t plus 1 is equal to wli at time t, plus we have the Hubbian term. So I have to compare the else output with the i's input. So this is exactly the same thing as here. But then we have a leak term, which is a bit more subtle, which is the sum of the k running from 1 to L of yk wki. So if we have a single output, this is exactly the same thing as here. If we have more, this is a bit more subtle. And in fact, we have some kind of what people call in neuroscience lateral inhibition. That means, you know, the direction, the PCA, the first top component, which is extracted by the first hidden unit here, is subtracted from the weights to the weights of the other ones. So that will basically make the evolution of the other weights in the orthogonal subspace to the first component. So these things actually, you can prove that this dynamics converges to a solution where the k weights you find eventually are equal to the k top components. If you have degeneracies between the eigenvalues, you will be somewhere in the space, in the top space. So we stop here and then I'll go to some.
So we have a 10 minutes break.
Comments about the calculation we have done and the study of Oja's rule. So one comment is actually not really a comment, it's an exercise, which I leave to your attention. So, so the rule was on the slide, but okay, it doesn't matter. So remember, Wt plus 1 is equal to Wt plus eta times Yt xt minus some leak term here. Okay? So, and I've always assumed that the learning rate was positive, right? Now, so my question is, what happens if you put a minus? So that's an interesting question. So think about it. That's called anti-Hebbian learning. And it's interesting also. So you can think about it, and we can talk about it next time. So the other thing I wanted to mention is that actually everything about this rule was we have seen that these things actually what it does is PCA. So PCA, we can see it as an optimization problem where we want to maximize over some vector here, so some components EI, such that the norm of a vector is equal to 1. And we want to maximize some function of the data. And the function is simply u of some of the I, EI xi, here, or let's say v. I will use v because I need this notation later. So this is average over the data here, and v of lambda is equal to lambda squared. Right? This is what I want to do. That extracts the top component. But written this way, you see that there is no reason why we should be interested only in v of lambda equal to lambda squared. We can use other potentials. In fact, people do use other potentials. For instance, you can consider the potential where v of lambda is equal to lambda to the 4. So what do we want to do by that? I mean, lambda to the 4 means that you, for instance, if I plot the projection sum over EI xi, and this is, okay, sorry, sum over EI xi here, and I plot the probability distribution function of this, so the histogram, I would like to find a direction in the space where this thing will be maximized on average over the data. So maybe the histogram of the projection will be something like that. You know, there will be peaks at very large value, so you cannot go to very, very large value. Obviously, you are bounded by the value of x, the norm of x. But in fact, if you maximize this quantity, you see the value for lambda close to 0 are not important at all. What you would like is to create large values, whether positive or negative. And this kind of things is very interesting if you want to do clustering, for instance. This direction would be able to distinguish two subsets in the data set, the one with very large lambdas, the one with very large negative lambdas. Okay? So this is some kind of things that people do. In particular, they have some settings like that for people doing what is called independent component analysis. Maybe I'll come to that later in the next lectures. So in this case, if you have v of lambda, which is not equal to lambda squared, but which is anything, then it's easy to see that Oja's rule can be modified to deal with this case. And the only modification is that instead of having, this is the Oja's rule, Wt plus 1 minus Wt is equal to eta yt xt minus yt Wt. That's Oja's rule. Then, in fact, what you have to do is simply to use the derivative of this potential. And if you do that, and you run Oja's rule, then the dynamics will converge to something which is actually solving this optimization problem. That can be shown. And it's interesting because there's no reason why we should do only PCA when we do data analysis. We may be interested in other things. Okay, so in particular, I'd like to, now in this second part of the lecture, so I won't have to finish everything I had prepared, but it doesn't matter. I'd like to go back to what I explained before, which was the phase transition. Okay, I have a problem here. Okay, it's going back. I'd like to go back to this phase transition here. This one, okay? So I just gave the result, but I did not explain anything. You remember what this phase transition was about, right? Okay, so I will give a more general framework. So you see, this phase transition is about extracting the right direction with PCA. So this is about whether the solution to this problem is aligned along the true direction. But now you can imagine the solution to this problem with any v, not necessarily quadratic v, and ask exactly the same question. Okay? So this is what I'm going to tell you about. And what I'm going to show is actually extracted from a series of papers from the beginning of the 90s. So there are 3 papers, one by Michael Beer, in, I think, Your Physics Letters in 1993. Another one by Tim Watkin and Jean-Pierre Nadal in 1904. I think that was in Journal of Physics A. If you want the precise references, just ask me. I can give them. Another one was by Heimann and Van den Broek. And there are two papers, one in JPhys A, the other one in Physical Review E. And this is in, I think, and the last paper is 1996. Okay? So I'm going to explain what they've done. Not all the details, but let's say the main steps of the analysis and the calculation, which is actually related to the techniques that were introduced by Pier Francesco. And you will see how this transition and other transition can be understood. And actually, you see a generalization of this phase transition. OK, so what they are interested in is exactly what I'm talking about. I've been talking about over the last 1.5 hours. So the framework is the following. We have some direction, which is in this paper is called the symmetry breaking direction. So I'm using the notation of the papers. So instead of calling this direction E, that is called B, so breaking direction. So it's in n-dimensional space. And I will assume that the norm of B is equal to n, or let's say the norm square of B is equal to n. So that means all the components of B are of the order of unity. This is what I mean by that. Actually, this precise direction does not matter, because everything is invariant to the rotation. So for instance, you can imagine that all the BIs are equal to 1. OK, so this is my specific direction, which is important. I want to recover from the data. So now let me generate data. So the data, I will generate samples, psi mu, which are in the same n-dimensional space, obviously. So mu will be the index of the data. So it runs from 1 to p, same notation as before. And I had to specify the probability distribution of the data. So I will assume that I have, let's say, some prior. So P0 of psi mu, which is some very simple distribution. So for instance, I will assume that all the components are independent random variables with mean 0 and variance unity. So maybe the mu index, I will put all the indices down. It's a bit simpler. And then I have a bias introduced by this B direction. So I will align these things along this B direction. So I will say that the P of psi mu, which is the distribution of the density of probability with which the psi mu will be generated, will be proportional to P0 times the exponential or minus of potential. So it's the same V as the V as mentioned before, of psi mu dot B normalized by square root of n. And D will be some function. It can be lambda squared. It can be any kind of function you can think of. And actually, the shape of a function matters a lot, you will see, for the results. So if you take lambda squared, you get this kind of phase transition. If you take other shapes, you get other phenomena, which are interesting. So, so just one moment here. You see B, the norm of B is square root of n. The norm of psi mu is, if I look at that, typically square root of n and so on. So saying that this thing actually matters, that means that the dot product between psi mu and B is expected to be order of square root of n. It's not expected to be of the order of n here. So essentially, psi mu and B, if you take them randomly, they would be orthogonal. They would be, the dot product would be of the order square root of n. And here I'm just biasing this a little bit. Instead of having some Gaussian variance here, what you would get if they were just independent from each other, you are expecting this to be, I don't know, maybe 10 standard deviation away. Okay? So this is not a strong alignment. This is some kind of weak alignment. Do you understand what I mean here? You see, if I look at the dot product between psi mu and B, the largest value I can think of is that this dot product would be essentially equal to n, if they were identical, right? Here I'm biasing over values of the order square root of n. So these are almost orthogonal, but I'm just biasing a little bit. So this direction is only weakly affecting the data. So it's not easy to find from the data. That's the point I want to make here. So example of V, if I want to go back to exactly what is going on in this transparent here, that's it, okay? If you compare this and this is exactly the same thing, with V of lambda equal to minus S over 2, 1 plus S lambda squared. That's exactly the case which was treated in this works, right? Here. But we can think about other potentials. So let me leave the potential here as I want, and then we'll talk about what happens depending on the value of the potential. Okay? So this is the way to generate the data, and now I want to make the inference. So I will make the inference using the Bayesian framework. So the posterior probability of the direction I want to infer, which in the notation of these papers is called J, that depends on the data. And it will be proportional to the likelihood of the B direction given the data. So it will be something which is proportional to exponential minus V of J dot psi mu over square root of n, and that should be a product of all the data points here, a product of a mu, so there is a sum of a mu here. Okay, so this is Bayes, and I will actually have also some prior over J. I will impose that the norm of J is equal to the norm square is equal to n, so it's the same norm as B. This is Bayes, but actually I don't have to be Bayesian. There are non-Bayesian people sometimes. So for instance, you have people who want to decode with maximum likelihood or maximum a posteriori. So in that case, you will introduce some beta here. And instead of doing beta equal 1, you may send beta to infinity, which means you find the best J, the one with largest posterior probability. You may actually also infer with a different potential V. This V is not equal to that one. For some reason, you may actually have some things here which may be interested if we have some prior information, about the V's. I talk about that. If we have prior information, this is interesting to incorporate this prior information here. So I talk about that. I don't think I'll be able today, but next time. Okay, so the question is the following now. I fix B, I generate some data points, and I'm asking what is the structure of a measure over the J's here. Okay, and the generating function of all the quantities you can think of is actually the partition function here, the log of a partition function. So which is the normalization of this thing. So the quantity I am interested in is the Z, which depends on the psi mu, which depends also on B, but I'm assuming that B is fixed forever. This is all ones, for instance, which is the integral over J, such that J squared is equal to n, exponential of minus beta V, sum over mu, of V J dot psi mu over square root of n. Okay? So now this problem looks like very much the problem that Pierfrancesco told you about. So I don't know how many of you followed the lectures by Pierfrancesco? Not everybody, so maybe it's important that I will go through things which actually are very similar to what he told you, I guess. So we want to estimate these things. If we are able to do that, then we will understand where are the important J's, where are the J's which actually contribute much or more to this weight here, to this partition function. And the question we ask is how similar they are to B. That's not the only interesting question. You may ask two questions. So one is the accuracy. So if I look at so for instance, maybe I should do it here. If I look at the space of J's, which is the hypersphere of radius square root of n, so let me represent that. This is the hypersphere. And B is somewhere. Okay? And the measure of the J's will be maybe concentrated around this. Okay? So maybe I want to know what is the extension of this. So given the value of beta, the larger beta, the smaller will be this domain here. So maybe for beta equal to infinity, I have a single j. And then the question is how far away they are. So I want to characterize the overlap between these two things, which I call R. Or maybe for finite beta, I would like to know the extension of this thing here, the standard deviation of a j, which is the precision. And if I pick up two solutions here in this domain, I would like to know what is the overlap between these two solutions, Q. So the two other parameters which will come out from the theory here will be this R and this Q. One is estimating the accuracy, the other one the precision, if we want to use statistical terms. Is it okay? Okay, so let's compute Z. And I will use these replica method techniques, which were very popular at that time. So if I want to compute the average value of R, for instance, so let's say j dot b over the square root of n over n, if I want really to compute the overlap, then this thing will be given by an integral over j with j squared equal to n of exponential minus beta sum over mu v of j dot psi mu over square root of n. And there will be a j dot b of n, and there will be a denominator which is exactly this z of j, right? Z of psi mu, sorry. Okay. So you see, I mean, as usual, when we have disordered systems, the psi mu, the disorder, I mean, the quench samples, they are in the numerator and in the denominator here, but I want to average the ratio. So one way to do that is to write this 1 over z as z to the n minus 1. So 1 over z will become z to the n minus 1. This is certainly true when n goes to 0. And now this z is at the numerator, and I can average over the psi mu. And for integer n, this is easy to do. And then we do this analytical continuation of n going to 0, and we get the expression here. So essentially what I want to compute is z to the n when n is small. Okay? So let's do that. So I won't do all the technical steps because I think it's a bit boring, but I will just give you the main steps of the calculation so that if you're interested, you can redo it at home or ask me if you have any question. Okay? Okay, so I need the last thing here. Okay, so we need first to, so I will go upward. So I need first to elevate this thing to the power n. So this is an integral to the n, so this is the n time integral, so small n. So z to the n will be an integral where I have, so A now is the replica index, which runs from 1 to small n. And I have the constraints of normalization for all the weight vectors. And this is the thing, sum of a mu and A, V of j dot GA dot psi mu over square root of n. Right, okay, so now, okay, that's the thing. Now, what I would like to do is actually average the whole thing over the psi mu, because this thing will depend on the psi mu, so we'll have an average here over the psi mu. So I will have what I call, I don't know if I have, okay, this big thing, n of n, which is the integral over the mu's, plot of the mu dic psi mu, mu I dic psi mu I. So and here is the measure. So that's the Gaussian measure I mentioned before. Okay, minus sum of the mu v of psi mu dot b times square root of n. Okay, so we have a measure over the samples which is influenced by the symmetry breaking direction. I use this measure, and I'm averaging my partition function over the j vectors, and this is what I get. So the n of n is this times z to the n of psi mu. So this is not normalized here. So I have capital N or curl N of 0 is the normalization constant. So I will divide by curl N of 0, but it doesn't matter. Okay, it's just a multiplicative constant. Is it okay? So that's the quantity I want to compute. So let me just sketch the main steps of the calculation. It could be useful for people not familiarized with replicas. So there are 5 different steps in the calculation. So the first one is to introduce the quantities we are interested about, which are the stabilities, which are the argument of these v's. You see, we have 2 v's. We have the v which correspond to the distribution of the samples, and the v which correspond to how j should align along the samples. And they are not at the same temperature. They can be at different temperatures, right? So, so I will introduce the stabilities, which are actually this dot product. But people call them stabilities in neural networks. And this is done by in some kind of brutal way. So I will use extra integrals, and I will write that 1 is a product of a mu of d lambda mu, d lambda hat mu over 2 pi, exponential I sum over mu. So let me just write this and then explain. Lambda mu minus 1 over square root of n, sum over I, psi mu, di. So you see the integral of a lambda hat mu, which is along the real axis here, is simply a delta function. So I'm just imposing that lambda mu is actually equal to the dot product between b and psi mu, normalized by square root of n, right? So this extra thing is simply 1. So I will insert the 1 here. And once I do that, then the argument of the v's will depend on this lambda mu, and the psi will be only here, so I can do the average of the psi very easily. That's the trick. And of course, I need to do that for the v's on the top line, but also on the v's on the bottom line here, or let's say here. So I need stabilities not only for b and psi mu, but also for the replica number a of j and psi mu. So these are the extra variables, product of the mu and a, dt mu a, dt hat, mu a over 2 pi. And this is exactly the same trick, right? Okay, so the t and the lambda are interesting quantities. And the t hat and the lambda hat are just extra variables which we get rid of at some point. Okay, so now I'm very happy because the psi mu are not inside the v's, which are complicated functions, but there are we have linear exponential term now, linear in the psi, so I can do the averages because I have a Gaussian distribution, which I cannot show, but this is here. That's the Gaussian distribution, right? So I can do the Gaussian integral, and this is easy to do. So I erase that. So this is step number 2, Gaussian integration. And this is the interesting physical point, because since the psi mu, this is the same psi mu which is seen by the weight vectors j that we are looking for, and the b, which is the right vector, then we'll get some effective couplings between the j and the b. So this is where the theory becomes interesting. Okay, so Gaussian integration, or let's say integration over samples. So we average over the data to get the effective theory. Okay, so we have the product of a I and mu, d psi I mu, And then we have a linear term, which is minus I over square root of n, sum over I and mu, psi mu, and we have, so if I don't make any mistake, bi lambda hat mu plus sum over a j I a t hat mu or mu a. So this is very easy integral because everything is decoupled. So we get just the square of that in the exponent. So this is equal to the exponent. Well, I mean, we have some multiplications, 2 pi and so on, but I don't care. Minus 1 over 2n. And we have the sum over I on mu, but let me just write the sum over mu and compute effectively the sum over I inside the parentheses. So we have lambda mu hat squared, and we have the sum over I of bi squared over n. Oh, sorry, maybe the n I should remove here and put it here. That's the first term when I expand this, right? And this is 1 by definition. So this is 1. Then I get the double product, sum over mu, sorry, sum over a, lambda mu, t mu he, so everything is hat, and I have 1 over n, sum over I, bi, j I a. Okay? And that's the interesting parameter. Remember the small diagram I had here? That was a dot product between the true direction and the one we get from the j's, which are sampled from the posterior distribution. That I call RA. So it's an interesting order parameter. So I want this thing to be large, actually, if inference is successful. And then we have a last term, which comes from this one. We have a sum over A and B, T mu A, T mu B, all hats, and we have 1 over n, sum over I, G I A, G I B, and this thing actually is another order parameter which is related, that's a QAB. That was the other parameter telling us how two different solutions I have sampled, I mean 2 different jets I have sampled from my posterior will look like. So that's related to the precision and this one to the accuracy. So there are nice order parameters. There are the things we would like to extract, actually, we would like to know about. OK. So I will introduce these order parameters. And I'll rewrite the theory as a mean field theory for these order parameters. So this is step number 3. So again, I will use the same tricks as before. So this is not the simplest way to do it. But this is the most general one, which can be used, for instance, if your vectors are not real valued, but they can be plus or minus 1. They can do binarized vectors. So the formalism is very general. In the case of continuous variables, we can do a little bit faster than what I'm going to tell you, but it doesn't matter. OK, so the order parameters. So the order parameters are coming out from the calculation. They are these RA, and there are these QABs. So let me again use the same trick. 1 is equal to the integral of dRA. I have a product here, dRA hat. And just to have consistent notation with my notes, OK, this is 2 pi over n. And I have and you have the same thing with the QAB, right? Do I really need to write it? I can write it, OK. I think it's there is so QAB is equal to QBA, so I can define this only for A smaller than B. And obviously QAA, if you look at the QB, oops, sorry, the QAA here, well, OK. The QAA here is just the norm of JA, which is n, divided by n, so it's 1. So there is no need to define this. This is 1. So the only interesting non-trivial quantities are for A smaller than B. So here the integration over Q hat and R hat is over the imaginary axis. But the saddle point will be for real values. So this is fine. Okay. Okay, so this is nice. And there is one more thing I need, is that I have the constraint over the norm of j's. And I will also write this as, no, so instead of having an integral over j which is constrained over the hypersphere, I will introduce this constraint as with some kind of thing like that, you know. So I will introduce the delta. So we have some integral over u a for each vector, exponential sum over a u a n minus sum over I j I a squared. Maybe with a 1/2 here, so there will be a 1/2 here. Okay. Anyway, so it doesn't matter. Okay? So I have all my constraints which are written like that. And then now I can rewrite the whole partition function, the whole thing I wanted to compute, and calculate it with the saddle point approximation when n is large. Is it clear? I mean, I hope it's not too fast. Or is it too fast? I'm just giving you the main steps of the calculation. Okay? If you want more details, you can go to the paper or ask me. But all the other steps of the calculation are very elementary. You want me to go slow way, or no? It's fine. But you should tell me, otherwise I won't know. Yeah, it's fine. Okay. Okay, so if I use all these things here, I can rewrite my quantity, which was this big curl n of n, which was the integral over the xi mu, integral over the j I a, and so on. So we have already done the integration over xi mu, but I had other extra integration coming from all these definitions now. So let me rewrite the whole thing. So we have an integral over the u hat a, which are there to impose the constraint, the normalization constraints over the j's. We have an integral over the qab and q hat ab. There are some normalization here, 2 pi and so on, but they do not matter for the leading order term in n. We have another set of integrals over the other parameters, the Ra and R hat A. Okay, and now, so where are all these things here? So they are already in the definitions. They are there, okay? They are everywhere here, so I should write them. So I have the first contribution, which is the exponential of n times sum over a u hat a plus sum of a smaller than b q hat ab qab plus sum over a r a r a. And then we have all the other terms. So the other terms, there are of two types. There are terms which depends only on the j's, and the j should be integrated out. And there are terms which depends on the lambda and the t's, which are the stabilities I introduced in the first step of the calculation. So I want to separate the two terms. Actually, these two terms were coupled, but they are coupled through the other parameters here. So I can really separate them. So the whole integral here depends on the other parameters in a very complicated way. So let me write the whole thing. First, we have this integral over lambda hat, and the integral over the TA and the t at a. So when I introduce these parameters here, these extra variables, they had a mu index because they depended on the index of a sample. You remember? But it turns out that all the integrals for all the mu's, they are all equal. So I have a single integral to the power of a number of samples. So there will be a big parenthesis here to the power of a number of samples, which is the power p. Okay, so what do I have? I have a 2 pi and so on. And so I have the lambda hat minus v of lambda. That is the potential I use to define my samples, to generate my sample. And then I have the same terms with sum over a, ta, t hat a. And here I have the minus beta v of ta. This is the potential I use to infer the direction. at the possibly different temperature. And then I had the result of the integration over the psi, which gave a Gaussian form for the lambda hat and t hat variables, if you remember. So if I don't make any mistake, this is exponential minus 1/2 lambda hat squared plus lambda hat sum over a RAT at A plus sum over A and B QAB T hat A T hat B. And the whole thing is to the power P. I hope this is readable. There is the whole thing is to the power P, the number of samples. Can you see the P? Yes, the whole integral here is to the power P. So here we are summing over all pairs of A and B, but it's obvious that QAB is symmetric matrix, right? This is implicit. So that's one part of the thing, and it's not over. We have also the other part, which depends on the J's. So I have so I will continue on the other blackboard. Okay, so this is multiplied by a big integral over the j's, so we have an integral. So the j's, when I integrate over the vector, actually I have an integral over all the components. And since I have introduced the normalization constraint through the u hat, now the components are independent from each other. So this is the same integral over n components, so it's one integral to the power n. Actually, this is not exactly true. It depends on the bi, but I will assume that b1 is equal to b2 is equal to 1, so I get n times the same integral. Otherwise, it would be a product of I of something which depends on bi. But the whole thing would be dependent only on the norm of bi, which is n. So I can go along one direction, which is all ones, and it's fine. So we have an integral of one component, but we have also the replica index. So we have small n components for each component I running from 1 to capital N. And the measure is this thing. It's a Gaussian measure, minus 1/2 sum over A U hat A J A minus sum over A R hat A sum over A G A minus sum over A smaller than B Q hat A B. Sorry, this is a square here. Q hat Q A B J A J B. And the whole thing is to the power of the number of components, which is n. Okay, so this is what we have at the end. Okay, so it's almost done here. So yeah. So I will just make a couple of remarks and we'll stop and we'll go on the next time, because otherwise it will just be too fast, I think. Okay. So a couple of remarks. So first of all, if we look at the integral of the t hat and the lambda hat, this is a purely Gaussian integral, so that can be done very easily. So what we end up here is some Gaussian measure. I mean, we have a quadratic form, a Gaussian thing, which is biased by the v of lambda and the v of t here. But the integral over the t hat can be done exactly, okay? So that simplifies a little bit the expression. Now, the whole integral here, also the whole thing here is actually purely Gaussian and can be done exactly as a function of all these parameters here. So at the end of the game, we obtain something which is, we have the integral over the u's, all the other parameters, so the r hat, the q hat, and so on, of something which is exponential of n. And we have some terms. So let me just underline the terms. We have one term which is coming from this part here. Oh yes, I always forget. It's a complicated thing. So this term here, which will be here. So this term is simply telling me that the interesting order parameters, which are the q and the r, I compute them through, actually, they have some conjugated forces, which are these hat parameters. So this is one thing which depends on this integration variable. Then I have a term, again, so let me, which is the yellow term here. This thing here, I can take the log, right, of this. So this term is a bit more complicated, but I have a log of this term. And the power of this, so this yellow, the power of this term is not n, it's p. And p is the, so if I multiply by n here, I have a ratio p over n here, right? So p over n is the number of samples per degrees of freedom to be inferred. And if you remember, this is exactly what I call 1 over r in the slides here. This is 1 over r. So in statistical mechanics, people use this ratio, what they call alpha, usually in the statistical mechanics paper. But this is the same thing as 1 over r. And then we have the other term, which is a purely Gaussian integral, so which can be computed easily here, which is the whole thing here. And the log of this is going to be there. Okay. Now, all these terms here, they depend on the other parameters here. And when n becomes very large, if we have a fixed ratio, for instance, here, then we can use a saddle point approximation, or let's say, to compute what is the dominant contribution to this integral here. So this is where I will start from next time. And once you have done that, then we have to optimize this functional of 5 other parameters here. 2 of them can be eliminated very easily, actually, analytically. So the only 3 of them. So the only interesting one are R and Q, which have a physical meaning, and we'll see how they depend on the number, for instance, of samples per degrees of freedom, and how they vary with the potential, which is the most interesting thing. And then I will say how we can go beyond that, how we recover all these results, how we do more than that, and how we could actually go even further if we use prior information about the J's, for instance, to identify more easily some directions. So it will be a start of the beginning of the next lecture, and then we'll move on more complicated things. Is it okay? I think I can stop here maybe.